Hello everyone, my name is Noah.
And I'm Alessandro from the Google Developers team.
We would like to welcome you and thank you for joining us today for GDG DevParty, an event organized by 5 Google developer groups in the UK and Ireland.
Now, while this event will of course be a bit different to your usual GDG meetup, we think it's going to be a lot of fun and perhaps a rare opportunity to get to know fellow developers from all over the UK and Ireland, and maybe beyond.
Although the current situation is far from being ideal, we are really excited to have so many people from all over getting together and sharing ideas.
It's fantastic that we are able to get together like this, even if it's only through our screens. And now, we will let the GDG organizers tell you more about them and kick off the event.
Enjoy the Dev Party!
So, just to introduce ourselves, this is the team that has worked to organize DevParty. We are a group of leads from a mixture of different GDGs, including London, Oxford, Southampton, Galway, and Milton Keynes.
Hello, I'm Bushra, and I'm from GDG Oxford, and I'm one of the moderators for the machine learning track today.
Hi, I'm Jason from GDG Milton Keynes, and today I'm working on the YouTube live streaming for this event.
I am Casey Nur from GDG Oxford.
My name is Karthik Nuli and I'm from GDG Southampton.
Hi everyone, my name is Oscar Macaulay and I'm from GDG Southampton and I'm going to be a moderator on the machine learning track today.
Hi, my name is Shadab and I am from GDG Galway.
Hi everyone, this is Jen Ashley from GDG London.
Hi, my name is Swapnil and I'm from GDG Galway. And today I will be giving a talk on Google Cloud storage options along with demos.
I'm Antoine Danois, Android developer at CityMapper, and I will be a moderator for the mobile track, and I'm part of the GDG London.
Hi everyone, my name is Goran from GDG London, and I will be one of the cloud moderators for today.
My name is Vladimir Salin. I'm a software engineer at Optelum from GDG Oxford. I will be a moderator on the cloud track.
Hi, my name's Eddie, and I helped put together this video intro. I have a YouTube channel focusing on open source. You can always catch me there.
So, before we get into the talks, let's just go through what you can expect from today and how the event is going to be structured.
As you're probably aware by now, the event is going to be split into 4 tracks running in parallel, each representing a different topic. Today we've got a great range of topics. We've got a track for mobile, one for cloud technologies, another covering machine learning, with the final track covering issues of diversity and ethics in the world of software development.
These tracks will contain 3 sessions, each session lasting 45 minutes. These sessions will contain a 30-minute talk and a Q&A at the end. When the Q&A is finished, there will be a 5-minute break to swap over between speakers. At this time, if you want to change tracks to listen to another topic, you are welcome to do so.
Once all the talks have finished at around 7 p.m., we'll then all get together in a Google Meet call for a party. This is meant to be a bit of fun where you can just chat to other developers that you might have met throughout the day and perhaps make valuable connections you wouldn't have otherwise been able to. Obviously, Not everyone has the time to sit and chat for a long time, so we'll officially end the event at 7:15 p.m. But those who want to stick around on the Google Meet call for longer are more than welcome to.
Here's another reason you might want to join the party at the end though. So those who tweeted out hashtag GDG DevParty throughout the day on Twitter and managed to join the party at the end will be in with a chance to win one of 3 prizes. We'll be giving away a Google Chromecast, a Nest Hub, and a Nest Mini to 3 lucky winners who tweeted out hashtag GDG DevParty on Twitter. So make sure to get tweeting and to join the party at the end, where we'll announce the winners.
That was a quick rundown of how our time together is going to be split up. But we highly recommend for you to go and have a look at the tracks and schedule section of the DevParty website. This will allow you to plan which talks you want to watch.
Additionally, I would like to explain how each track will be organized in terms of what platforms the talk will be taking place on and how you can interact with the discussion.
The sessions will be held on YouTube Live, with the link to each track's livestream being posted on the DevParty Slack channel. For the link to the Slack channel, see the DevParty website, where there is a link to join under the How to Participate section. This means you can seamlessly switch between tracks after a talk has finished by closing one live stream and opening another through the links provided on Slack.
YouTube Live will allow you to post comments so that you can ask questions throughout the talk, which will then be read by the moderator and posted to the speaker. Please do understand that the speaker might not be able to answer every question due to time constraints. So obviously, please be sensible with your questions. We want to make the session as interactive as possible, so please don't be afraid to put forward your thoughts and engage with the talk throughout the comments.
So, thank you for listening. We hope you have a wonderful time and gain some great insights into whichever topics you choose to explore today. If you encounter any problems, please let us know through the Slack channel. But for now, get comfortable and wait for the first talks to begin.
Welcome to the DevParty.
So, hello everyone. On behalf of GDG UK and Ireland, we are very excited to welcome you to DevParty, an online event that offers interactive talks and workshops from experts in a range of fields and provides a great chance to connect with other developers from all across the UK and Ireland. So, a bit about us. I'm Oscar Macaulay from GDG Southampton.
And I'm Bushra Lamadi. I'm from GDG Oxford.
We're your hosts for this track. So before we start, just a couple of housekeeping things. So in terms of content for the track, there will be 3 sessions, each with a 30-minute presentation and 15 minutes for a Q&A. The Q&A will be essentially that you write your comments throughout the talk when they come up, or you can write them during the Q&A session at the time. And we will present them to the speaker, and the speaker will try and answer them. Obviously, we might not be able to answer every question, but yeah, please feel free to ask your questions all the way throughout the talk on YouTube Live. For the code of conduct, please see the link. It would also be great if you could tweet about the event or use any social media with hashtag GDG DevParty, but especially on Twitter, because at the end, we'll have a party where we'll announce our prize winners. So those who tweet out hashtag GDG DevParty throughout the day on Twitter and manage to join the party at the end will be in with a chance of winning 3 prizes, as you might have just seen beforehand. So we'll be giving away a Google Chromecast, a Nest Hub, and a Nest Mini to 3 lucky winners. So make sure to stick around for the party at the end. You can see the description for the link to the party, but it will open at 7 p.m. and we'll put the link at the end of the sessions as well. So I'll hand over to Bushra now. Oh, sorry, no, I should just go through the agenda as well. So, yeah, so obviously this day is split into 4 tracks. We'll have a mobile track, a cloud track, this track, the machine learning, and the ethics and diversity track, all running alongside each other, each with 3 talks. So you can switch between tracks for different talks. You don't have to stick for one throughout the whole day. But yeah, we highly recommend you check the DevParty website for the full agenda, where you can see the content of the talks and decide how you might want to spend the evening. For this track in particular, we're about to hand over to Marc in a minute for the first talk of the day. He's going to be talking about machine learning in the Google Cloud. Then at 5:30, we'll hear from Dr. Larissa Suzuki, who will be talking about productionizing machine learning. And finally, we'll hear from Sergii Khomenko at 6:15, who will be giving a talk on machine learning for developers, a practical approach. So now I will actually hand over to Bushra.
Thank you, Oscar. I'm very happy to introduce our first speaker in this track. So Marc is a software engineer working on Google's developer relations team in London. His mission is to build tools, demos, tutorials, and other educational artifacts to make computing and data science more accessible and inclusive. Before joining Google, he spent 30 years building products and managing engineering teams in the telecom industry. We thank Marc very much for joining us today, and I will hand it over to him.
Thank you, Bushra. Are you able to hear me okay?
Yep, all good.
Cool. Okay. Well, thank you for having me, and to both Bushra and Oscar. And also, I'd like to thank all the participants online for spending part of your Saturday with me. As noted, I'm going to go through some material on machine learning in the Google Cloud. Now, I normally use this as a kind of a workshop where I do a hands-on learning lab, but that obviously takes a bit more time than the 25 minutes I have allotted today. So I'm going to give you access to the lab, and you're welcome to do it on your own. Let me know if you have any problems with it, etc. But if you're interested in a deeper dive or more intensive hands-on training in this domain, feel free to get in touch with me, and I'll leave some contact information shortly. I'm always happy to come to companies, organizations, meetups, etc., schools, to help people get a firsthand experience with this technology. One thing to note, the slides that you see today are all available online at mco.fyi/mltalk. And I'll keep those around. This is me. My Twitter handle's there, my email, and my blog. Feel free to reach out if I can help you with anything. I didn't mention this, but my job is basically to help people understand how to take advantage of the Google Cloud in both business and education. These are today's goals. I'd like you to come away from today with knowing a little bit more about what machine learning is all about, a little bit more about the basics of neural networks, and some of the tools and techniques we have available to make it easier for you to use machine learning in the cloud. So let's start with some foundational items. I often like to explain, and forgive me if you're an advanced person, I'll go through this section quickly, but I like this sentence to help explain what machine learning is all about. This sentence is normally written, the quick brown fox jumps over the lazy dog, and I've written it as the brown quick fox. And for most native English speakers, that sounds odd. And it's actually, in fact, not just that it sounds bad, it's a grammatical error. And you might wonder, well, why? If you're not sure why that's a grammatical error, you're in good company. I think, in my experience, less than 1% of the population knows why it's an error. Most people know it's an error, but don't know why. And the reason is because there's a very strict set of rules about the order in which adjectives and sentences should be arranged. And the interesting thing about this example is, as I said, most native English speakers know that sentence was in the wrong order, or the adjectives in that sentence were in the wrong order, but they don't know why. And so there are things that we know that we don't know we know, or we don't actually know the rules behind them. We just have a sense for what's right or what's wrong. And the reason is because of pattern matching. We've been exposed to these rules in normal usage so many times that we've just sort of acquired, it's almost like in our firmware, we've acquired a sense of what's correct. You know, it's quite a different experience for someone who's learning English as a second language and has to try to internalize all those rules. And that's really what machine learning is about on a software basis, is we're teaching software to learn from not only the rules, there's still an element of learning from rules, but it's a very big component related to learning from experience and exposure to data. just like we learn chess when we're young or at any age, really. So I like this quote. Alan Turing said it in 1950. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? And that's really at the heart of what this revolution has been all about, is teaching software to learn things in a very similar way that we teach young children to learn, like things like language and so on. So if Turing said this in 1950, why is it all of a sudden, why did it take until 2010 or something to really take off? And the reason is that there's been what I think of as a perfect storm, a number of factors that have changed the entire landscape in the last, I would say, 10 to 15 years. One is the developments in hardware, specifically GPUs, have had a huge impact, which were not originally foreseen for this purpose, but were used for games and video rendering and things like that, but have turned out to be quite important for the computations that we do when we're building neural networks. Cloud computing has changed the game quite a lot. It used to be that if you had a very expensive computation you wanted to make, you would have to buy or somehow get your hands on large numbers of parallel processors. And nowadays with the cloud, for a fairly small amount of money, you can quickly harness tremendous amounts of CPU and then just give it back and stop paying for it when you're done. There's a lot more data available thanks to things like GitHub, the web. Open source has made it so that a lot of the refinements and algorithms and techniques are now available almost instantly. So all of these things together have contributed to this huge sort of renaissance in the field of deep learning. And within Google, we've seen this quite noticeably. Deep learning models, and I'll explain more about what I mean by that term, have come to not just be a cool feature, but really an essential aspect of every product. You can point to any product on this slide, and I can tell you some really important way that we're using deep learning to solve user problems. The graph you're looking at is a graph of the number of unique projects using deep learning models, primarily TensorFlow models, in the Google source code tree. And you can see it's a pretty strong, it's actually quite a bit out of date now, but it's been a pretty strong exponential curve. This is a graph of Arvik's papers going through 2018 that were related to machine learning, and we're seeing that same curve. So it's really been explosive growth. I'm sure you're all aware of that. But I'd like to switch gears now and talk a little bit about what's the mechanism behind this growth, what we're actually talking about when we talk about deep learning and neural networks. So the diagram at the top is showing how we've done things for the last 50 years of computing, where we try to codify rules using classical programming languages. We take data in and we give out the answers based on those rules. And machine learning has sort of turned that upside down, and we take the answers and the data, and the software tries to infer these rules from looking at the data. And the way I like to think of that machine learning bubble you see there is, I think of it as a black box with a bunch of dials. And there's some mathematical function that will map any set of data and answers to some set of rules that will generalize as well as possible across data it hasn't seen before. And the magic is turning those dials just so. And we're going to take a closer look in a moment as far as how those dials actually look in the real world and how we turn them. But that's the basic idea. So let me jump to a small visualization notebook that I quite like to help make this visual. Let's think about this function here. Let me try to blow this up a little bit. This is what we call a polynomial. It's a bunch of constants times some power of x, and then we sum them together. So this would be a third order polynomial because the highest exponent in this expression is 3. And what this notebook is letting me do, first of all, I can change the order. So let's go up to a fourth order polynomial. And then I can tweak these slider bars here to get different coefficients. These are the 5 coefficients you see in that polynomial expression. And what I can then do, so the way I'd like you to think about this is imagine you set these sliders to define your unique polynomial. And let's imagine that it's a secret and the computer wants to guess. Now, obviously the computer already knows because you're using the computer to select them. But let's play along and imagine that the computer doesn't know. So what we'll do is we'll click this guess button. And all that does is generate a random polynomial of the same order. In other words, it's generating a random collection of coefficients, just like the ones you've selected, 5 in this case. Totally random, and it ends up with a totally random fourth order polynomial. You can keep doing this as often as you want. But now we're going to click learn, and you'll see what happens. It's going to start with the guess, and it's going to use a technique called gradient descent to move closer and closer to the target. And it gets pretty close pretty quickly, but the interesting thing is these endpoints are still a little bit off. You can keep running, learn, and it'll converge, get closer and closer. Down here we have how many iterations of the learning algorithm we've tried and what the loss is. And the loss is a measure of how far away we are. In fact, if I reset, do another guess, let's set the number of iterations all the way down to 1. And let me make another guess, because that guess is starting out a little too close. I want it to be a little bit further away. Okay, so we'll do learn, and you see it starts with the guess right away. And the loss is 0.47, so almost a half. And I'm just going to click, and each click is getting closer. If you keep your eye on the loss figure, it's now 0.12, 0.06, 0.03, and so on. And so you see something we often find in this field is 80% of the convergence happens in 20% of the time. The first few iterations often get you much closer, and then the last, 80% of the time, or 80% of the iterations, is giving you that extra 20% of accuracy. What I want you to do is take a look at this notebook when you have time, and it explains how we actually do this. What's happening here is we're using something called gradient descent, which means we calculate a loss, what's called a loss function, which is how close or how far is our guessed polynomial from the actual polynomial. And then we take that loss function and we perform something called a derivative on it, which gives us the rate of change as we move around on that curve. And there's actually a nice visualization I can show you here. To finish my statement, we use this derivative to figure out what direction to move to get closer to the target. And the way I like to think about this is it's giving you insight into how to turn the dials on that black box. Otherwise, you'd just be reduced to randomly turning them and hoping you get closer. This is the math we use to tell us exactly how to turn them and how far, which ones to turn and how far. So the thing I want, one last thing on this visualization is if I go to a first order polynomial, so that only has 2 coefficients.
Mark, can you just zoom in? Sorry, can you just zoom in a bit?
Sure.
Thank you.
Better? So a first order polynomial has only 2 parameters, and that means it's going to look like a straight line. And we'll do a guess here. And what you're seeing down here is a 3-dimensional graph of the what's called the partial derivatives of the loss function. So this is the actual function we're trying to optimize, to minimize. And that little orange ball is where we started with the guess. So when I click learn, I want you to keep your eye on the orange ball. And I think I can, yeah, cool. I can turn this around so you can watch it from this angle. So interesting, nothing happened. Let's try that again. Guess and learn. Okay, so the demo is not working right now, but what you would see if it were working is this orange ball would sort of slide down this hill into the valley, and that's why we call it gradient descent. It's a way of figuring out how to move that ball downward, and each time we move that orange ball, we're turning the dials for the parameters. So hopefully that gives you a sense. I'm sorry that didn't work, but hopefully that gives you a sense of what's going on when you see this converging. So back to my slides, and oops. This is a more elaborate description of what's happening when we do these functions. I'll kind of leave this because I think I may have spent a little too much time on that last demo, but basically the idea is we turn the dials, that's changing the weights in these transformations, and we compare the predictions with the true targets, get a loss function and a score, and then we optimize and we keep kind of iterating like that. The lab exercise, as I said, we're not going to do, but I'm going to share the link for you. The lab is based on TensorFlow. If you've not used it, it's a great system to know about. I don't claim that it's the best or the only one, but it's one that's been very well tested inside Google. We use it quite extensively, and it's developed a very strong following throughout the industry. So definitely worth taking a look at. TensorFlow.org is where you can learn more. I highly recommend using Keras, which is now a part of TensorFlow. So Keras is a higher abstraction level on top of TensorFlow, and I find it's much more intuitive and user-friendly. So I'd strongly recommend you start with Keras and go down to the lower levels of TensorFlow if and when you need to get deeper into it. This is the link to the lab. I'll show you very quickly what that looks like. It's a Jupyter notebook hosted on a service that Google provides called Colab, which I could talk about on its own. It's something I really enjoy working with and authoring notebooks in, but this is just one example. You're welcome to come here, and if you do visit this notebook, you can save a copy in Drive, and it'll make your own private copy of this notebook. And what's happening here is it walks you through the MNIST problem, which is where you have these handwritten digits and you want to recognize in a generalized way which digit you're looking at from these sort of hand-scrawled digits here. Here's some examples of digits and their labels. And then we start with a good network that's just very primitive. It's about the simplest network you could possibly create. And it gets to 93% accuracy in its validation testing, which is not bad for just a completely naive first approach. Then we get a little bit better by adding more layers. And this is showing you what Keras looks like in the wild. You actually build these neural network layers as if they were Lego bricks that you kind of snap one on top of the other. And again, in the workshop, I can get into more information, more details, and I'll leave you to discover more about it in this lab. But this is doing better now. Whereas we were at 93 or 4%, we're now at 98%, which is great. And as always, the extra mile gets harder and harder, but this is a much more elaborate network with all kinds of tricks and advanced techniques. It's still not huge, but as you can see, it's much more involved than the previous example. And when we run that, we get to 99.45. And there's a way with TensorFlow, there's a tool called TensorBoard that lets you actually visualize the training graphs. I don't see them, or maybe they're below. Yeah, there it is. So these are the training graphs, and you can see the good. I'll go with the validation's more important than the training data. So that's the curve for good validation. That's better, and that's best. And so you can get a sense for how your training is proceeding. And in the interactive workshop, I actually have my audience run these models and build these networks with me. So it's a lot of fun. And then finally, you generate an interactive widget like this, where it's actually using the model you built to figure out which digit you're drawing. And so the idea is, it takes the information from the data it saw, and it's now applying, based on the way you tuned those dials, it's now applying its inferences on digits no one's ever seen before, right? I'm doing new digits that no one's literally ever seen before. And it seems to be guessing pretty well. I'll leave it to you if you can fool it. It's actually not that hard for some technical reasons, but Anyway, back to the slides again. And okay, so that's a very quick background on ML, how we're using it in Google, and how we build these networks. What we're trying to do in the cloud is to make it available and easier to use for everyone. This is one of my favorite quotes. This is Tim Berners-Lee, the inventor of the World Wide Web. And he famously said about the web that this is for everyone. And I feel very, in a similar way about machine learning. It's an extremely powerful technology like the web, but we need to make it available for everyone. It can't be this thing that only PhDs in computer science get to play with. And so that's one of the things I'm most happy with about Google, is that we're introducing a lot of new products in the cloud to make it easier for you to use these technologies. This is a summary of all the different cloud capabilities, and this is actually not even up to date. This is, I think, from November of last year. The list is even longer now. So that's incredibly cool, but the downside is there's a lot of stuff there, right? And a lot of the things that I don't like about software development are that I have to worry about all these other things going on with, or at least I used to, with my system, installing software, security, scaling, all that kind of stuff, when all I really want to think about is my problem. And that to me is what's great about the cloud, and especially some of these machine learning services that we're providing now. A lot of them are designed to take the administrative burden and the setup and the maintenance and a lot of those other things that I don't want to have to worry about. Take that away from you and let Google manage that for you, and you just really get to focus on your solving your problem. Some quick examples. This is the Vision API, where this is a pre-trained model of imagery where you can send an image up and it will analyze it and tell you things. I did this a few years ago. It said it's a person, it's a man, and then it came back with this, which I thought was rather rude. And it said I might have a hairstyle, which I don't quite even know what to make of that. But fortunately, I just found today the same image returned smile and travel. So they've stopped trying to guess my gender, and they've stopped asserting that I'm a senior citizen. So I think that's progress, a small amount of progress. Something called AutoML has actually been a huge innovation in the last few years. The idea behind AutoML is that rather than hand building these neural networks and fine-tuning what they call the hyperparameters and the structure, wouldn't it be cool if we could have neural networks that build these for us? I mean, the computer's better than we are at a lot of things. Why wouldn't it be better at finding just the right mix of all these structural elements to build better neural networks than we can by hand? And that's proven to be the case. This is showing progress on some important image processing benchmarks over the years, and how the AutoML has managed to do better, outperform the human authored networks with less cost, less computational cost. So it seems pretty clear that this is going to be an important innovation. And at Google, we're trying to make the AutoML capabilities easier to use and more available for people, so that you don't have to think as much about how to build the network. You can just specify the problem and we'll generate a network for you. This is an example of a model that looks at chest x-rays in children. So this was a pediatric pneumonia data set from Kaggle. And if I can just jump over to the AutoML platform, or console rather, you can see what this looks like. So I have a model called X-ray pneumonia. And here what I've done is I've uploaded all of these images and I've labeled them as normal or pneumonia. And there are 5,800 images in total, and they're all labeled. And you might think that's a small data set, but the idea behind AutoML is, one of the key ideas is transfer learning, where you start with a very rich model for image processing, for object detection and sort of image processing capabilities in general. And there are certain features and capabilities built into that network that you can leverage, and you can essentially refine the output a layer from that network. And so you can start with something that's extremely rich. Maybe it's built on millions or billions of photographs. And then you add just your small amount of data. Here, 5,800 may not seem small, or it may, but it's not a huge amount of data. And you can fine tune the model using transfer learning to get a much better result. And the interface here is quite nice. You can see the training results, you can see the evaluation, you can actually test it interactively. So if I say upload images, I'll try to do this quickly. Here's a bunch of do normal x-rays. So I will sweep them out and it'll upload them. And now it's sending those to the model I predicted. And it's saying 92% confidence rate. This one's normal, 99, 96, 83. Here's one that gave it trouble. It's quite ambivalent about this one, 53%. Here's 76, and so on. I can do the same thing with the pneumonia x-rays. It does about the same, to be honest. But very cool that you don't need to know anything about TensorFlow or Keras or neural networks. All you need to do is have a bunch of data and have it labeled appropriately. And you can just let Google build the model for you and deploy it and everything else. Another really cool example of that, and I'm getting a little bit low on time, so I'll finish up in 1 second. But another really coll example of this is AutoML tables. So if you have just tabular data, comma-separated values, or whatever representation you have this data in, we have a product called AutoML tables, which is quite interesting. You basically send the table to this service. It parses it for you, divides it up into all the columns. Here's an example. I took the Titanic data from Kaggle, and it's parsed out all the columns, told me things about it, like what percentage of the data was missing, whether it was null valued or not. And you select one field to be the target. So I've selected the survive, which is a categorical binary field, 0 or 1, whether you survive the Titanic disaster. You upload your data and you click train model, and you don't have to think about which model to use, because Google is going to generate ensemble models, decision trees, boosted trees, all the cool technology that people are using to do these sort of categorical analyses. And similar to the AutoML Vision example, you get some nice statistics back when you're done training, and precision and recall and so on. You get a confusion matrix. And then you can test your model interactively. So what you do is say online prediction, and you get all of the fields here. And this is giving me pre-populating with some sample information. I'll say predict, and this person, Miss Emily Rugg, tells how much she paid to be on the Titanic, her gender, her age, and so on. It says she would have survived with a 0.872 confidence level. If we click generate feature importance, that will tell us how strongly the given features impacted her survival, her result. So that's it in a nutshell. If you have tabular data and don't want to become a machine learning expert, you don't need to. We can build a very strong model for you with just a few mouse clicks. And this shows that recently, a lot of the Kaggle competitions, Kaggle is a place where machine learning experts and people who just want to learn ML come to experiment with solutions. And actually, primarily, it's a competition site. So they have prizes, and you compete to who can build the best model. And this is showing the blue bars are AutoML tables. This is not meant to imply universality or every contest is being won by this service, but it's doing quite well in what would seem to be a pretty high level of competition. That's the primary material I have. I have a bunch of resources, which I'm skipping over right now, but they're more than you just saw there. But I just hid them for now to jump through them in real time. But I invite you to come to the slides, take a look at all the material. And as I mentioned earlier, all my contact information is there. The slides will be around for a while. And yeah, feel free to get in touch with me if I can help you in any way. I'm happy to take questions at this point.
Great, thanks, Marc. That's a really great talk. So we've had quite a few questions from the audience. I'll just go through. So Supriya asked how to link the ML prediction models developed using AutoML to ARKit.
Yes, so I think you're able to export the weights from your models, but I haven't tried that. So that, I think, that would be the way to integrate it. I don't have any experience with ARKit, so I'm not sure exactly how I would do that, but my approach would be to export the weights, the TensorFlow model weights, and then see if ARKit has an import function for those weights, or if there's some public domain AutoML or TensorFlow to ARKit. The models that ARKit is using can be exported in a standard format. H5 is the one I've been using.
Great, thank you. And next, Bryn Jones. Can characteristics of the data being input be used to determine how many dials are used by ML to determine the rules, or are all dials you've used and the influence of some are just set to 0?
So by the dials, we're referring to the weights in these neural networks. I didn't show a picture of the neural networks, but they're typically built with layers. And the number of nodes or neurons, or there are different words for these entities, but the number of independent elements tends to go down as you move through to the end. And the number is typically a tuning parameter of the kind of information you're trying to process. For example, with imagery, you want to do something called convolutional networks, where you're kind of scanning the input across a fixed subset of the input pixels. And typically you'll define what's called channels with each subset. And then you'll have different ways of pooling them together. So the number of dials is really a free parameter as a function of your input data, the size of the space you're working on, and also how you're trying to tune this model. So there's no real hard and fast rules about where the dials are or how many there are. It's more of one of these. To be honest, most people who are really into these building and tuning these networks are just following what has worked well for other people. I think in general, machine learning and deep learning in particular has been more of a engineering than science, I think, is the way I think about it. Good practices and less, I think we don't understand a lot of it as well as we should as far as basic science and math.
That's great. And next we hear from Silky NG. So when you train a neural network, the more data, the better it gets. But he's heard that too much data and it can become specialized. So can you explain why that is and how we might get the right balance?
Yeah, so I think Silky, you're referring to this phenomenon we call overfitting, which is where you have a network that is so good with the training data, but it doesn't generalize to data it hasn't seen before. You can think of an extreme example being a neural network where you have one node for every input. Let's imagine you're processing images and you have a binary simple classifier that says, is there a cat in this image? I'm going to do the thing that everyone does and use a cat, internet cats as an example. Let's assume this network says the probability that there's a cat in this image. Now, if you had 10,000 images, you could have a 10,000 node network, and each one would fire when it saw that particular image. It would sort of just know those images. It would be 100% great at the training data. But then when you threw it an image that hadn't seen before, it would be terrible. And that's what we call overfitting. And it's not really a property of overfitting, doesn't tend to be a property of how much data. I don't think there's a notion of too much data. I think it tends to have to do more with how you build the network. There's various techniques. There's sort of this dance you get into where you get better and better accuracy, but then you start to overfit. And the way we normally deal with this is we hold some of the training data aside and we don't let the network see it. We do all the training, or at least one round of training through the entire training set. And then we run it through the validation data that it's not seen up to that point. And if we find overfitting, the fingerprint is usually that it did very well on the training data and then suddenly didn't do so good on the validation data. So it's more of a function of the approach than the data, than how much data you have.
Great, thank you. So we can probably fit in a few more questions. So we've also heard from Chris Michael. He asked, are there any planned changes to make it easier to integrate TensorFlow Lite models into mobile apps?
Yeah, I think there's been a lot of work going on to make it easier to use TensorFlow on a mobile app, on Android in particular. I'm not a mobile developer. I'm more of a web and server type person by background, and my primary interests are in those domains. So I can't speak to that directly, but I know some folks who are quite active in that area, and I'm happy to connect you up with them if you'd like to reach out to me.
Great. And finally, we heard from Satya Sashi. Hi, Marc. What would you suggest to a beginner to ML with basic math and stats to try to get a good understanding of machine learning?
Good question, Satya. I would highly recommend a book by, I'm looking to see if I can find it here. It's basically the Keras book. I think it's called Deep Learning with Python. It's by the guy who actually, I'll get it on the screen here. I kind of hid all my resources slides to zip through the talk quickly, but this is it. This is my favorite deep learning book. It's a fantastic resource. It's by Francois Chollet, who is the author of Keras, the high-level library I mentioned. And the general answer beyond that particular book that I would share with you, I get this question a lot, like, what should I study? I want to get into machine learning. Should I focus on math? Should I focus on statistics? Should I focus on Python programming? And I think that, in my opinion, the best way to get going is to pick a problem and to try to start working with it. Because I think if you start with the notion of like, I want to learn all there is about linear algebra, which is a really important subfield, it's hard to keep that going. And I find it much more helpful to pick a small problem. And Kaggle's a great resource for this because it has all these cool problems. Think of something, think of an idea you want to work on in this field, and then just start trying and see how far you can get, and let it be more goal driven. That works best for me.
Great. And we've had another suggestion from Vanny in the chat as well, just for anyone else who didn't see that. A great resource for learning is Maths and Stats for ML. So there we go. Great. Well, I think we can wrap up there. Thank you very much, Marc.
My pleasure. Thank you.
Thank you, Marc, so much.
Thanks all.
So we will move on to the next talk at 5:30. But in the meantime, we'll have a little break. So in that time, we've ended quite early here. So you can switch to another track in the meantime if they're still going on. But otherwise, we look forward to seeing you for the next talk at 5:30, where we'll be hearing from Dr. Larissa Suzuki on productionizing machine learning. It should be a really great talk. So we'll see you then. Thank you.
So welcome back, everyone. So we're about to start our next session in the machine learning track at GDG DevParty. So our next talk is about productionizing machine learning by Dr. Larissa Suzuki. She is an award-winning computer scientist, inventor, and entrepreneur. Her career includes over 11 years advancing many fields of computer science and engineering, including smart cities, data infrastructures, immersion technology, AI, and computing applied to medicine and operations research. She serves as an honorary research associate in the computer science department at the University of College London. She is a recipient of many, many awards and honors that I cannot give them all justice. So I'm very happy that you can speak at our event, Larissa, and thank you so much. And I will hand it over to you.
Thank you very much for having me. Can you guys all hear me? Okay, I hope so. Okay, so I'm here today to talk to you guys a little bit about productionizing machine learning. Most of the time we think about machine learning as something as just like writing the code and that's going to be ready to be in production. But in fact, that's not that easy. And I will give some introduction not only on technical terms, but also on what is happening on the market in case you want to start your startup or in case you want to understand how the industry is working at the moment. So the key takeaways is why is that so important now? Why we all need machine learning so much? Use cases in enterprise. Key issues when we productionize those machine learning systems in production. And the steps for us to consider to winning ML products and making sure they work in production and they're going to be fit for purpose and mirror the users we are building them for. The first thing that I would like to talk to you a little bit is about the market demand, how important it is. So a lot of research has been done in the past years, and we saw a huge trend about using machine learning. So 8 out of 10 companies, they are using machine learning. And it's expected that the savings and the business value of machine learning is going to be much over $1.2 trillion. And machine learning is also expected to increase productivity in companies by 40%. So also giving them not only huge profit, but also savings in operation as well. And why is it happening just now? So one of the things I will talk about is about the hardware, the computing, but also about the data, because machine learning is all about the data. The data drives the behavior of the system. So we see that we have a huge increase of data coming from users. So our personal data is going to exceed 5 terabytes. By 2020, each one of us will have all that information online. We have 30 million new devices connected to the internet every single week. And 40% of all data we're going to use will come from sensors just this year alone. And it's expected to increase very, very much. And this is, I'm not sure how many of you are familiar with the Internet of Things. So the Internet of Things have been driven by many different things. The first one is the Moore's law, that is the capacity of the transistors, they would double over time, and also the cost of them would be reduced pretty much. We also have the power of the network. The more nodes you have on the network, the more powerful your network and the data collection enrichment is. We have advancement in big data technologies, in databases, NoSQL databases and servers, and also machine learning framework advancements, and also different like platforms for us to serve systems in productions like Kubernetes. So if you look on this graph here, the dawn of connected machines, by 2050, we're going to have 50 billion devices for 8 billion humans. So we're going to have a lot of devices giving us that information. And the good thing about this is that it changes everything we see around us. And so we are not limited anymore on how we can collect and process that information. In the past, this is how traditional multi-proprietary systems they worked. So for instance, you would have one application A and B. you would need a proprietary ICT infrastructure to connect to each of those applications. And a dedicated device could talk to that particular proprietary ICT infrastructure, especially because of like protocols and different messaging systems. So for instance, if you look into a building, we have systems for fire, for elevators, for fire, for security, and they are all fragmented, and you have to go to multiple dashboards to see all that data together. The good thing about the sensors and them being available so much, and the ability to connect a lot of data, and also the power of 5G coming up that enables us to transmit much more data, is the ability to repurpose asset. So in this case, it was just a lamppost before. Now we can enrich this with multiple sensors that can collect lighting, can connect flood levels, and we can share those information across multiple systems, and including our machine learning software that we want to build and to deliver new products to consumers and users. So this is the ability of the converged system concept. So we get all that data and put together for our users. The problem that we see today is that the data volume is increasing, which is good, it's not a problem, but the complexity of the data is not becoming so the complexity of the data is very, very low. Like the number of data that's going to have low complexity is very low. So we're going to have much more complex data for us to deal with, especially because of multi-structured data, images and videos. And when we work with machine learning, especially like different types of like machine learning, so convolutional neural networks that we have to process image, we're going to have different types of images or frames of videos. So the low complexity of that data is going to be much low. Most of the data will have high complexity. As people working with machine learning or interested in machine learning, there are many opportunities, and I would like to focus a lot on this. Why is that important? So every single year, we throw away 100 billion just worth of food. We throw away $500 trillion worth of water every single year, watering the food we're going to throw away. We have 1 in 9 people around the world, they are undernourished. And every 15 seconds, a child dies because they have nothing to eat. So we produce a lot of food, but the food cannot get to people. We have the cost of 1 billion pounds is the cost of congestion. And we are going to have 2 billion cars on the streets in the next 10 years. And we humans, we spend 4 to 6 months of our lives trying to find a parking space. And it's a huge problem for us because we are humans, we are so expensive. We should be able to spend our time doing better things. And we have cars that are not used to its full capacity. When we talk about autonomous vehicle, which will depend a lot on machine learning, a lot of people think about, oh, I'm going to just read my magazine and enjoy my time. But when we look at the humanity, we see that 65 million people, they are on wheelchairs, and over 200, nearly 300 million people, they are visually impaired. And they're the people who are marginalized and could make the most benefit of autonomous vehicles as well. We have a lot of investment on R&D, creating fancy cars, but not much on traffic system. And the traffic systems are where we're going to collect the information, the data from, and also the objects on the streets, and reason about what we are seeing around so the autonomous vehicle can work and operate and take person from point A to point B. So there's a lot of opportunities, and air pollution is another one that is also cost 100 billion pounds every single year for us. And 92% of people are exposed to very high level of pollution, and pollution causes us a lot of issues, not only with our lungs, but also cognitive impairment and inefficiency in the cities and our systems and the way we do businesses and in transport are the main cause of that. So we have 3 million people dying every single year because of air pollution. So data can really give us the ability to do something about it. However, when we look about the adoption of machine learning in industry, we see in this graph, for instance, nearly 60% of industry, they're still doing research and development. 25% are still on piloting. 6% of industries, they are actually implementing and putting some planning on something for production. And only 6% of industries across the globe, they have actually machine learning assistants deployed in production. And why is that? Because machine learning is not only about the code. So if you see this graph here, the source here is from Google. There's a very nice Google paper about the hidden cost of machine learning. So the ML code is just a tiny bit of everything we need to productionize our systems. And the machine learning models today are still being deployed with significant human intervention, which makes the development very, very slow, difficult to standardize processes, and we are more prone to introduce errors in our system. So we need to look into machine learning into a broader scenario, not only about the code, but about how we validate, how we analyze, how we do our feature selection and engineering. Everything in yellow is done offline, is at the time we do the pipelining. And when we serve in production, we have a live system, then we must monitor. We have to have our proper workflow. When do we serve? When we retrain? We have to serve at scale and scale according to the number of users. We must deploy according to the environment that we are deploying, and also have self-adaption. So if we have different models running, we can pick the best one. We can self-adapt also to anomalies and outliers that we detect at runtime. So we have to think about this, and that's why it's so difficult for us to productionize machine learning. It's not only about writing the algorithm, that is just a tiny bit of this. And I would like to talk to you a little bit more about that. Another thing that makes it difficult for us to productionize machine learning models is not asking the right questions. Most of the time, we see people, oh, I want a machine learning algorithm that is going to give the best treatment for this cancer patient. Most of the time in industry, what we see in reality is machine learning, for us to come with a response for that kind of problem, we need to have lots of tiny machine learning problems to be solved. So for instance, the first question for this, what is the best treatment for cancer, could be, is cancer present or not? So we have a detection problem. Then we can move into a classification problem, another machine learning problem, that is what type that is. Then we can do a segmentation algorithm to look at to what extent is that present into the body of the person, and make a prediction on what is the likely outcome given all those variables and what that particular cancer represents. We can use natural language processing also to look to the historical information we collect from the person, habits, for instance, if the person is alcoholic, or if the person is diabetic, or also the genes of the person. Then we can make a proper recommendation of the treatment and the likelihood of the treatment to work. So not asking the right questions and break down the problems into small, tiny things makes very complex for us to build something so huge and productionize that to the users. And this is where we have to start changing how we see machine learning. So this is a traditional life cycle. So let's start with the yellow side. So the first thing people do, we collect the training data. Then we prepare that data. We clean, we train our model, we evaluate, and then we have our model. And on the purple side, we have our model in production. We serve this on the production environment. Then we serve. Then we have inference data. So we are collecting real data from the user. And that inference data can also be collected to serve us to retrain our model. So linear process, we collect data, we train, retrain, put it there. So this is the traditional way of seeing this. There are many questions we have to ask at each of those individual steps. So for instance, when we prepare data, what features can be derived from that data? Are these features being generated? What are the best practice to transcode values for machine learning? So shall we use one-hot encoding? How do we get to converting that data for our machine learning model to interpret. So other questions that we might have when we train and evaluate is the model good enough? Am I using the right metrics? Am I selecting the right features for this? Should be more data, more features, less features, more data? There are many things that we consider on this, but several iterations later, we follow the same step. We train, we prepare the data, we have a model that we feel like, oh, it's great, fantastic, let's serve this. When we serve, we get inference data, we provide the predictions, we collect the inference data, and we can use that to retrain our model. Then we serve again, and then we have this linear process. So let's see how that works. And by the way, we're just touching on the ML code here. We're not looking at anything else. Okay, so if we execute and productionize this, let's give a very simple example of a data failure. So we have a developer that is updating a piece of code that has a machine learning system inside. So same features, same data, same training, same serving logic, everything is fantastic, the same. I'm going to commit that code, but out of nothing, we have incompatible binaries, and that will result in a feature to have the wrong value. For instance, a feature will have the value of -1. Poof. This is what happens in production. The model performance will go south. It's so difficult for us to identify where the error came from, and it might just come from incompatible binaries, from the data, from the retraining, or from the pod failing. It can come from anywhere. So for us to retrain and to identify where the error is quite expensive. That's why we cannot see a machine learning system as a kind of just a linear process. It's very interactive. It's a lot of iteration, and it's not in the same way that we develop traditional systems. So very quickly here is just other examples that happens when we have problems in data. Because one thing we have to understand is in software engineering, the code drives the behavior of the system. If this and that. In machine learning, the data will drive the behavior of the system. So all the time we see users, yay, an AI tool for me, let's use it. So when you have imbalanced data, so you have like more data representing certain people than others, what can happen is we are not be able to classify or identify certain features to distinguish people from one another. So for instance, Apple, to unlock the phone, most of Chinese people could unlock each other's phone because the number of the classes they had was so unbalanced that they didn't consider much people with Asian features, so that didn't work quite well for them and could not identify their features quite well. So we start having users very frustrated with this kind of system. And we also have racist classification system as well. That is when we have bias inside of our system and we don't look into bias. And we also have, I don't know if you came across, but also Amazon had some problems with candidate selection system as well, and also LinkedIn as well. So LinkedIn, when you had a female name with CEO, for instance, that would correct you and tell you, did you mean a masculine name, then CEO? And the problem is like it's a bias, and most of the time we assume that, okay, if I remove the column gender, that will unbias my system, but that's not much the case. We also have to make sure whether we can get our prediction and predict back the gender. So there are many things that we have to make sure we put into place to ensure there's mistakes does not happen in production system. Another issue that you guys can go and research is about the Amazon Prime same-day delivery service, which they use data from many different places, but somehow some of the data they consumed based on postcode related the postcode of being of African Americans, and those African Americans had data related to them that they said they were poor, they could not afford same-day delivery service. However, most of the people in these gray regions that they are not served with Amazon Prime same-day delivery, most of those people, they were Prime customers already, There was no reason whatsoever to not give them the same day delivery. But it's basically not checking the data that you have. And that is very dangerous because that impacts the lives of people. So we have to have a lot of care into productionizing those systems, because the system will learn from the data we give it to. So users get frustrated, and we have to understand how we can launch our ML solutions in a better way. So the first thing I would like to talk to you it's about some of the best practices in understanding the problem, validating the problem, modeling, evaluating, serving, and also improving them when we serve this to the user. In this slide here, I have divided the process of building a machine learning system for production in 3 different steps. One is the dev pipeline model, that is you do offline on your computer, is the exploration part, is where you do your data validation, you do your data splitting, your transformation. And we also have a part that will play during the offline process when you are coding, but also in production. There are the times that you have to revisit your model in production and make sure that you can select a different model. You have to retrain your model at scale. You have to validate and collect metrics at live time. So this middle column are everything that applies when you're doing your experiment offline and also when you're doing that in production. And in production, when we look into that column, we have the deployment of the model. We also have to look into serving this model properly so that we have the consumers getting the service that are catered for them. So we don't want, for instance, Coca-Cola being able to access the API that is serving the predictions for Pepsi. We have to make sure like we serve them and put all the security in place, which is quite important. We have to monitor our model, our data, and our system at runtime as well, and create alerts. Because one thing we cannot do is, if we have a machine learning model in production and then we have 1 million customers, we cannot hire all data scientists to be checking the system. So we also have to put into place it's good practice alerting systems. So for instance, if I define particular thresholds that my model cannot perform below certain thing, we can receive alerts or outliers as well. If we detect some outliers that could be a fraud or something, we could also receive alerts regarding this. And also model optimization that can be done at production time. We can have assembling competing models running in production, and then we can pick the best one. And I'm going to go into more details now with those ones. So the first part I said is about understanding. That is about when we get the data. So this part of the machine learning pipeline, the offline process where we are collecting data, maybe mock data for us to start looking into our problem. So data can be ingested in batch process or streaming, and we can integrate with Spark, Hive, HBase to collect that data from. The thing that we have to bear in mind is there are many ML frameworks available that allow us to do many of the sanity checks that we have to. We have scikit-learn, we have TensorFlow, we have PyTorch, and we also have Jupyter notebooks that allows us to integrate all those things and use them together. The best practices for sanity checking, understanding data, and ensuring that data is good at the collection time is try to automate as much as possible what we can. So automate, auto-detect the types of data that you're collecting, if that is numerical, categorical, auto-visualize the statistics of the input of the feature. So for instance, one of the things that I am a director for product management, and I work productionizing machine learning at Oracle. And one of the things that we do is it's mandatory. The visualization of the statistics is not optional because we then visualize the shape of the data. It's also good practice to visualize the percentage of null values, because if you have a lot of sparsity in your data, you might have to look into a model that can be really optimal for data that is quite sparse. And also check the consistency of the values, if there are many outliers, and also the dependencies on the features. So on the understanding part of collecting, those sanity checks can be quite helpful for you at the beginning. The second stage that is still on the offline part is the validation. That is all about like, let's do our feature engineering and select our best features. So it's about autocorrecting, removing complete data, also understand a little bit more about what data is irrelevant, redundant, or highly correlated, because one thing that is quite good for us is to reduce the size of the data that we use in production. By reducing the dimensionality of data also helps us with performance, not only performance in terms of hardware and serving, but also performance of the model as well. When we look at the model part, as I said, like there are many ML library that we can use and process in any language. So when we look at the model training, the best practices that we have is when we use those types of like supervised, unsupervised learning that we have labeled or unlabeled data, is to make sure we divide them into train, validation, and testing. We have the right percentage for that division, that we ensure that our data is balanced, so we have good representation of all the classes that we have. So for instance, we are going to classify 3 different types of flowers. We should have like very good like representation for all the classes there. Also, I said about the dimensionality reduction as well to ensure higher performance in your results, and also model selection as well. In practice in industry, most of the time XGBoost wins, but it's still like a good thing that they can do is on creating different algorithms and combining them, creating and assembling of the results of those models. And then model training is done when you are doing your offline process, and also when you productionize this as well. In production, that is what we call the model retraining. For the evaluation, best practices, model debugging, and evaluation that is relevant to your model. We see a lot of time people just using AUC for any type of model. AUC cannot tell much in many cases. So if you're using classification, make sure that the evaluation metrics you use are relevant for classification. For regression, the same. I also watch for overfitting. The key thing for us to understand how to test and monitor machine learning is that it's different from software engineering. In traditional software engineering, we have our code, and we check behavior, do integration tests, a unit test, and then we put the software in production. That is the running system, and then we monitor that system if that is receiving too many calls, if that's coping with demand. That is software engineering. In machine learning, the data drives the behavior of the system. So we have to test the data at all the time. We have to test the data at the time when we do our code, at the time that we serve, at the time that we train and retrain in production, and also at the time of model serving. So testing data while we serve the model is quite good, because we can see if there's any change in the shape or distribution of the data, because that will impact the performance of my model. And that is when we can have different alerts or retrain our model, or reconsider different models that can be better suited to the problem that you have. The orchestration part is the part of how do you serve the orchestration of your machine learning model in production. So it's about, first you collected data, then you train, then you serve, then new data come in, then you retrain the model. So it's about having that particular workflow. There are plenty of tools that are open source that are great for this. So Argo events, they're very good for orchestration of workflow. And you can do this with Helm charts if you run on Kubernetes. And that allows you to also integrate with CI/CD, which is quite fantastic, and rolling in different ways. You can have canary deployment, do A/B testing before you actually put that into production. And also facilitate your versioning your model and your data, and also doing the proper rollback when something goes wrong in production. This is an example. This is about serving. Serving is about the machine learning model in production. So we have TensorFlow serving. So if you are writing your code using TensorFlow, and if you're not using TensorFlow, there is also something called a tool called Seldon. Seldon Core allows you to configure and deploy a collection of services, machine learning services, as APIs and host this for any customer to query for prediction. So you can have just a model and an API and customers calling this, or you can have more complex product graph. Product graph is your machine learning model in production. So you can have different models, you can have feature transformation on the running model at the live system. You can have outlier detection that you can send to a different route, to a different model, or to an alert system. And also explainability as well. So Seldon Core is something that is quite interesting if you want to take a look into, and they are also open source. Finally, the model, the system, and the data, they have to be monitored at runtime. So runtime checks and monitoring is quite important for us, and it has to be something done at all the times. So I put here a graph, an example of Uber Michelangelo platform. So they have like the confusion matrix, the precision recall, all those graphs for data scientists to visualize how things are going to production. So there are many dashboards that are available that are open source, and they're very production grade and used across industry. So there's Grafana. For monitoring alerting services, there's the Prometheus family of products. So if you have a long-lived container, for instance, an API providing predictions at all the time, you can use Prometheus to collect your metrics. If you have short-lived containers, that is just for training a model and that container is killed, the metrics of that retraining might not be cached for a long time for Prometheus to be able to scrape. So there's also Push Gateway, which is a tool provided by Prometheus, so that can cache your metrics until Prometheus has the time to collect that metric and persist that for you. And for the runtime checks is all the assessment of the metrics against the thresholds, and also to make sure that you understand the cost of a wrong prediction. What is the cost of missing a fraud, or what is the cost of recommending a banana instead of an apple to a customer? So making sure that you understand the cost of a wrong prediction is something that is quite important, that will help you to put into place optimization and also detections on the live system that will enable you to serve your customers much better. The lesson I would like you guys to take away, besides understanding the market, the complexity of serving things in production, and the best practices, is that garbage in is garbage out. You cannot jujitsu your A out of bad data. If your data is bad, is biased, no matter how awesome your machine learning algorithm is, there's nothing you can do. And your data is not going to be providing your customer with a very good model that will generalize well enough to give amazing products for our customers. So that is what I had to talk to you guys today, to give you a brief overview of the complexity. And I recommend you to take a look into papers from Google, The Hidden Cost of Machine Learning. That's a very good one. And there are many tutorials also on the internet on using Kubeflow. That is also a tool that enables you to productionize machine learning from beginning to the end. So thank you very much for your attention and for attending my session. Thank you very much.
Thank you very much, Larissa, for a very interesting talk. I mean, I approach machine learning from a research, so it's very, very informative to learn about how it's used in production. We had a couple of questions come up. I'll take the first question from Supriya. So Supriya is asking about cybersecurity of Internet of Things devices with the advent of the quantum computing, as current cryptography is limited. She wants to hear more about how machine learning can facilitate machine learning.
So in terms of cybersecurity, that is a very difficult topic for me to kind of give much of the opinion on how the machine learning can facilitate on this. because this is an area that is really evolving, and with all the limitations that we still have into testing this and experimenting this is something that I cannot give much of an answer for this on how it can be helpful. One of the things that we can do is to use machine learning to train systems to go and to try to test and to break into IoT devices, and to see what how robust the new things coming with quantum computing can be.
Brilliant. So Supriya, I work in cybersecurity and I use machine learning. So if you have any questions, I'm happy to take them on Slack or just direct message me. But thank you, Larissa, for answering. One question from Satya. She's is asking, can they have access to the slides if that's possible?
Yes. So what I'm gonna do is I will put the slides. I will host the slides, and I will tweet with the hashtag of the event, and then with the address. So who is interested in having this presentation can just go and download and have access to this.
Brilliant. Another question from Jonathan. What are the best practices around removing data from the model where it's based around pseudo? I don't even know what
PII is PII data. Yes, so PII data is the personal identifiable information, and that is something really, really crucial. And one of the things that we have to make sure is like all complying with GDPR, which is something that in certain cases in the industry that I work for, so for instance, in human resources, use cases for machine learning, for instance, content matching or that kind of things, we have the permission to use this. But to remove the PII data is more about understanding which are the data that is considered to be PII. So it's about understanding how the GDPR works and or other laws of different legislative regions. So for instance, name, address, everything that can identify someone is considered as PII. And then that is a matter of you either hashing. So one of the things that we do, we might not remove, we might just hash those information. And then so that information is not usable or understood by anyone.
Brilliant, thank you. Another question from Aladu. Can you give more examples of bias that and other defects in machine learning models?
Yeah, so for instance, when we talk about the bias, we have so we have the bias of we have the bias that we have from the data that we see. So for instance, we have the bias, for instance, if we collect data about, for instance, you are doing a candidate matching. So you have certain CVs and you have certain jobs. So you look into your prior applicants for that jobs and the ones that were successful. And you might identify that people with CVs with certain words, they were very successful and they were hired. If we use this and do not check whether all those people, they fit into a particular segment, for instance, they are all men or all women, or they are non-white, that can introduce a bias in terms of the language that they might use. So your algorithm will learn how to, for instance, dismiss other CVs that could be very good for that particular position. You also have acquired bias that is, for instance, from chatbot for interacting with users. So for instance, the one that we had from Microsoft that Ty learned how to repeat something that was very bad from users as well. And we also have bias that is also introduced by us, by humans, into not only on the raw data, but also on the recommendation that we might make. So we might accept or not a recommendation, for instance, for a woman to take a job or for someone to go on bail or not. Although the system might say the person might go on bail or let the person go, if the person has a bias inherited into the person, that person can override the machine learning decision, and then we'll introduce bias again into the system. So we have multiple ways of having that. And what we have to ensure is that we do not learn too much about the features. And so in TensorFlow, I know they have introduced something quite new that does not allow us to learn too much about the features so that we can generalize it much better. And that will also introduce safety into getting bias of learning too much about certain things and only thinking that those features are the unique ones for us to consider on the machine learning system that we are using.
Brilliant. Thank you so much again, Larissa. If you have any follow-up questions or any more questions for Larissa, she'll be happy for you to connect on her Twitter account. We also have our Slack, so do post any follow-up questions or discussions. I know Nikolaya had a question. Unfortunately, we don't have time to answer that. We will have a bit of a break. When we are back, we will have our final talk from Sergii on machine learning for developers, a practical approach. Until then, thank you very much again, Larissa, and make sure everyone to keep tweeting, and we will see you all in a bit.
Thank you, guys. Any questions, please tweet me, send me on Twitter. I'm happy to take them and to answer them there. Thank you very much for the opportunity. It was amazing being with you guys today. Bye.
Thank you very much. Bye.
So welcome back, everyone. It's time for our final talk of the day. And our final speaker in this track is Sergii Khomenko. He is a VP in product engineering at Stylight. He is also a Google developer expert in machine learning. He founded a machine learning meetup in Munich, Hacking Machine Learning. And currently, his meetup has 2,000, more than 2,000 members and has hosted over 29 events. He believes in paying forward as well as open science and open source. As a result, he frequently engages with the community by conducting workshops, giving talks, and contributing with code. So, Sergii, thank you very much for joining us today. We look forward to your talk. Over to you.
Thank you. It's really exciting to be part of this community. Unfortunately, it's a bit of in different locations, but I guess it's also enabling us to do quite a bunch of things. So I'm really, really, really excited. And today we have seen already quite a bunch of different amazing talks, right? And they were also approaching it from different perspective, right? So for me, it's also nice to wrap it up in slightly different, from different way, right? Because usually, we have seen one talk about cloud, right? And how get familiar with machine learning. We have seen something about how to get into production, but you can also imagine if you read some stuff about machine learning, or maybe you just heard some hype around that, and sometimes it's still a questionable, hey, but how do I approach it, right? Where do I start? Where do you, where do you get the data? And how do you see it end to end? And this is basically what my talk about. You're going to be a bit of more on the quick side, but you're going to hopefully see quite a bunch of interesting points there. So you already gave me a good introduction. I guess the main point of or something that goes through all of those sentences, right, and paragraphs is basically that I like to get my hands dirty and try it out, right? And given that we were on this quarantine mode quite a bit of time, and we spent a bit of time indoors, I pick up a new hobby of doing a bit of robotics. And here you can see a tiny robot that is in virtual environment following the ball and doing these things, right? So what I guess want to say is that people can study different subjects for years, right? Or you can just start playing or hacking with something. So that's basically the main theme of my talk as well today. So, but I still get money for working somewhere full time, and this company called Stylight, where we have a big e-commerce platform that's essentially live in 16 countries and has more than 25 million products, right? So I see sometimes not only this hobbyist approach, right, but also our production task that we're having in order to solve those problems. So the talk is going to be a bit of a connection of those two. And as I said, this time frame is pretty small, right? So we have one talk, and the amount of information that I would like to tell you is quite a big number. So sometimes you're going to feel as it's a jump from plane, right, where you're definitely enjoying that. You definitely see many colorful things, but it's hard to focus on one particular thing, right? Otherwise you're going to miss entire fun of this journey. So don't be afraid by seeing amount of information that's happening there. Just remember those nice and scenic places, right? And you can always come back to them and go a bit deeper. Yeah, so what is agenda essentially? An agenda, how structured, I will bring a couple of examples of something that I consider exciting examples of machine learning. I would touch point a bit of on TensorFlow, and after I would guide you through a couple of end-to-end examples and what lessons I had. And it's gonna wrap up with a couple of more practical examples. So hopefully by the end of this story or this talk today, you would be way more comfortable of starting something, and maybe next weekend you're going to build something exciting on your own, right? And after, as Marc mentioned earlier today, that maybe you're going to pick up your own close to your heart project and develop it something really exciting. But in general, again, we only going to have 30 minutes today, right? So I definitely advise you to go to the internet, right? Get a couple of online courses, especially because right now most of them are free or available, and community just amazing and phenomenal. So it's also a couple that I have on the screen, but you can definitely find different ones. Yeah, and machine learning. I've seen that Marc already was giving you introduction, but I truly love this picture because for me it's also showing a bit more from a fun perspective, right? you have like machines and they kind of like learning just like from the name, like what does it mean, right? Where are they learning from? Is it like from each other or from data? And a couple of examples that I brought to you, right, just like to extend it a bit more, right? Because if you come in from more, I don't know, like scientific literature, right, you might be seeing, hey, we solving like some health problems, right? Or if you come in more from enterprise, maybe you do some like advertisement predictions and you see some problem solving there. But I'm gonna show you a couple of like very diverse set of problems that might be visual in this case because it's easier to convey them, but they might be still pretty interesting for you. So first one is, yeah, here you can see basically two sides of the screen, right? One is more original image or like original video, basically, and another one is something that neural network would translate to a different weather conditions, right? And one can wonder like, hey, this is cool, but what is application? Where do we need to have that? And if you have seen all the news about autonomous vehicles, right, and how things are developing in that directions, this is like really big topic nowadays, right? The only problem, as all of those like neural networks, they need to have like lots of data to train, right, and to be confident that things gonna work as they should be. So you have like two ways, right? Either you kind of like go like a Tesla way, right, when you have huge fleet of cars that can collect it, right? Or you have something that neural network can generate you a synthetic data set, and after you do some additional work to translate it from one to another. Or here you can see also work by OpenAI, and OpenAI built, yeah, like basically artificial intelligence, if you want, that can play games, right? And yeah, it might sound like, hey, but like what is the application of that? But practically, if you think about action space in this game, right? So there's like, it's enormous, right? You have like different pixels, you have different actions, right? You need to have like not only just like next action, but more like long-term strategy. And this also can be solved with machine learning. And we have seen that we can, you know, win against like the strongest players there as well. Here's also a funny example again, when we have a source video, like in the left corner of some musical video, right, and they're doing dance. We have some neural networks that can detect different, you know, poses basically and joints of our body. And after we have like another general adversarial networks that can generate, given our image, right, how we would look like in this like a dancing setup. And it actually looks pretty fine, right? So maybe finally if somebody was afraid to get some dancing career, it's going to be like a good setup to get you excited about that. And I could go on and on, just like last few ones. Here, the famous painting, right, that definitely didn't have like any video recording back then because there was no technology. But again, like by us having like a huge amount of data on, I don't know, like on the internet and YouTube, for instance, right? By us designing like a good architecture of the network, right, suddenly we can actually infer this information, right, and make Gioconda actually, you know, like be live and doing some actions. What is also worth mentioning that those three, you know, moving pictures of Gioconda, you can actually see, say, different behavior, right? So it's actually, we can enforce to get a bit of like a different way of this person to behave, right? And it's pretty interesting. It also has like different implications. How do we validate what is real, what is not, and all question of like fake news is also popping up, but it's like just a funny part of that. And the last one, you know, you can even go like extra mile when you know, you can generate faces, right? You can try to do some speech to text, right? And after, if you add like even more work on that and a bit more data, right, you can even make those drawings from the past, right, or pictures from the past actually synchronize their like lips, right, and they're going to be like singing.
Those walls are built, oh baby, they're tumbling down, and they didn't even put up a fight, they didn't even make a sound.
So suddenly you have Rasputin doing a bit of like Beyonce. What else can you see like on Saturday afternoon, right? Yes, and I will again like touch point a bit more on you know, like what is the difference and why everybody is like so excited about this like machine learning thing, right? And it's something that Marc already did mention, so I'm not going to go like much in details, just like very shortly, right? So imagine you're a developer, right, and you got this amazing idea from somebody to build the activity detection, right? And you have some sensors, right? So you can try to infer like what is the speed of the person, right? And you can build like some code and be like, hey, if speeds are less than something, you'd be like, hey, this is most likely walking. If it's not, it's maybe running, right? But after, if you need to add like biking, it's kind of like a bit more complicated. If you have whatever, like golfing, it's got like way harder, right? So all of that Marc already did mention, right? We coming from paradigm, right, when traditional programming has domain experts, right? And those experts are able to codify some algorithm, right, that given the data can give us some answers, right? And if you look a bit more to machine learning, especially supervised machine learning, it goes like another way around, right? We have some data, we have answers that we would like to have, right? And after machine learning, that generates the rules for us, right? And I think it's kind of interesting, but it might be not really that exciting, right? Or you'd be like, okay, so what is the deal with that, right? But practically for me, how I think about that is if you would have like automatization back like in Industrial Revolution, right? And it like enabled us to do quite a bunch of things, right? In many cases, programming is also like, a multiplier for people's work, right? How fast they can execute. And in this case, like machine learning, right, can go like even extra mile, obviously for limited scope, right? And instead of like multipliers, it's almost like, exponent to that, right? Because some things can be developed basically just given them the data. Yeah, and after our activity recognition is basically we have a bunch of time series data. We say like, hey, this is like walking, this is like something else like is running, this is like biking. And after this thing, it's just like after using this algorithm, gonna learn basically from there, or find some patterns in the data and build some model around that. So how can we do that, right? And there are like different ways, right? Different libraries on the market, but something that's close to my heart is TensorFlow, right? And if you look at TensorFlow, most likely, there is like hard to find in 2020 person who haven't heard about TensorFlow. But why for me TensorFlow is exciting, because it's like fully open source, right? And community is just like enormous, right? Meaning that if you wanna build something, right, you can really go to the code and be like, hey, how does it work, right? What is the situation, right? And we even had like with my community here in Munich, something called TensorFlow doc sprints, right? When we were just like sitting on like one of the Saturdays as today, for instance, and we're just like reading code, right? And trying to deepen our knowledge like on these approaches. And meanwhile, you can still improve it like for entire ecosystem. So I think it's pretty cool and pretty nice to have it. Yeah, but in general, TensorFlow has like different layers, right? There's like a parts that are, responsible for like working or an accelerated hardware, like as GPUs or TPUs, right? So there's this like notion of execution graph, right? So you have some operations and you would like to run them. There's some different front ends, right? That you can interface from Python or from C++. And there's like a bunch of different like layers as well, right? An idea how you can read this graph is the higher you go like in this table, right? The less like number of lines you would like to write. Simply saying that if you have like some candy estimator, right, you simply need to have like one line and you will get some simple network to go. If you want to go a bit more and more advanced features and you, I don't know, like do something like custom, you can always go a bit deeper, but you need to have a bit of more time and like knowledge about that. But what I want to convey with that at the end of the day, you decide like what you would like to go and how deep you would like to go. And this, I think, is pretty cool. Plus, what started as just like a framework ended up being like an entire ecosystem, right? So you can run it like on different devices. You can scale it and do like other things. Okay, so this was like a bit of introduction of like more general pieces and what I'm talking about. And now we're gonna go a bit of like into examples of you want to build something, right? And what it takes for you and like what are the like helpful things to do, right? So as you can imagine, if you're talking about from this paradigm that you need to have like data and labels, right? Data is kind of like essential part of this discussion. So you definitely need to have it. And there is also this notion of garbage in, garbage out, right? That very common in machine learning communities, that if you have like really good data, right? Your model is very simple, you most likely can find some really good answers, right? But if you have like, if your data is really like horrible, right? And you want to try like a good model, sometimes it's fine and you can just like find some signals like out of unstructured, but in many cases you also kind of get like not really good results. So paying attention to the data is something that is very helpful. Not even talking about like ethics, right? Just like in order to get it to work, right? So be really careful on that. So if you have your own idea, right, and you want to build something, right, where do you get the data, right? And I mean, in the ideal case, if you're a corporation, you already have like a bunch of data points, but even in that regard, first, like sometimes it's like hard because the data that you're collecting not always the data that you need afterwards to run those inferences, right? So like a couple of places, and I'm gonna show you examples, right? So one of them is Kaggle. Kaggle is like a big data science and machine learning community. They run some competitions, and you can learn and benchmark your skills basically. But they also have big amount of data sets, so you can just like try and see maybe there's somebody uploaded already data sets that might be helpful and a good starting point for you. There's also a bunch of data set just like by scientific community and like other corporations. Examples that I brought to you is called Common Objects and Contexts, right? Or COCO, right? And those are like really also helpful. Maybe there's some of labels that are helpful for you, right? Or you can just like use it for starting point, right? The same goes for open images. And what is interesting with open images, because like in the last couple of years, Google started to also add different diverse images, right? So they're coming from different like backgrounds, from different countries, from different, I don't know, like levels of income of people. Because in many cases, all of those data problems are because we're collecting it like from first world countries, right? And we're trying to solve like problems like elsewhere, and after it doesn't really solve it, right? So there were open images, especially with 6, right? It's pretty helpful to get some data there. Plus there's like TensorFlow dataset as a library that giving you like really nice and approachable way to get the dataset, right? So Marc mentioned this MNIST dataset, so basically handwritten digits. And in order to get this dataset, you can just simply like import the dataset basically in Python, and after say like, hey, I would like to have MNIST, and it's pretty easy to get it outside of that. Plus, there is also Google Images, right? Especially if it's just your hobby project and you want to get something going in the beginning, it's a good starting point. So at some point, I had this idea of checking how much healthy, not healthy food I'm taking, right? And after I built something with that, right? So in order to get the dataset, haven't found anything already structured, so I started just to use Google Images for a good starting point. As a developer, you might be coming from different like languages and different paradigms. So just to explain where machine learning is currently right? So there's like a big majority of projects are coming more from Python. Like there's still like different work in Swift, right? Or like in R, but I guess like Python would be pretty helpful for you to know that, right? And again, Python is like pretty friendly for beginners language, so you can get pretty far away with that. There is also Google Collaboratory that allowing you to, I don't know, in a browser, basically run some notebooks without actually having it like stored locally. Plus it has like support for Google Drive and like other pieces, right? Additionally, many people are afraid that, hey, I don't have like hardware, I don't have like GPU at home, so how can I train those like big networks? And Google here providing you for free also accelerators as GPU or TPU, so you can train things like relatively fast. Okay, so like a part of this talk is basically based on a workshop, similar as Marc mentioned earlier today, that I was given like in different places. So in case you want to have it like somewhere in your community, just like approach me later and we can figure it out. But just to give you a context, I was working with different like type of sneakers, and that's like where like the problem is basically coming from, right? And I also want to say that this is like more coming not for production grade machine learning, right? It's more like to get your hands dirty. And after there's like more examples how to make it a bit more exciting, right? Or production ready. So one of examples of that is there's like a nice article by Andrei Karpaty called like as you can see, a recipe for training neural networks, and there he goes like a bit more, what does it mean, right, and what steps are, right? I guess like if you just like wanna get your hands dirty, right, I wouldn't suggest to go like super deeply like in all pieces, right? Something that is like definitely super helpful, right, is setting up some pipeline, right? So by you changing different parameters, you can definitely see the results without actually doing things like manually, right? Because in general, all of this machine learning and deep learning as well in general, having a bit of a more engineering approach currently than more science, right? So you need to go through different space, right, of ideas, validate them, and just like go step by step. That's why it's helpful to have something on more software engineering side that allows you to pretty quickly change it and come back to that, plus some other things as overfitting organization, but I think like you will learn it a bit later. Cool. So what does it take? Okay, you got some data set, right? And where do you start? So usually you start like reading this data and getting this data processed, right? And you can do it like more manually, or TensorFlow providing what's called TensorFlow Dataset API that has a nice feature as, for instance, like automatically scaling that for you, right? So here you can see number of parallel calls is basically can be auto-tuned by the library itself, right? Because if you just do something very straightforward, you might end up that it takes like quite a bit of time and it's running like in single thread basically, so it takes like ages to process. Plus there's also like a format called TensorFlow records, right, that allow you to binary store your preprocessed data, right? So meaning like you once do normalization of your images, right, and after you store this like TF record, and it's like way faster to read afterwards. I can also share with you some notebooks how to make it like more convenient and how to get like full power out of that. Additionally, as I mentioned, usually your training and preprocessing kind of like goes hand in hand, right? So you have like a batch of images and you need to like work with them. So, and if you don't do it like properly, you might have a situation where first all of your like CPU is kind of like doing work, and after your like whatever like GPU, right, that's trying to train it, right, and it's like you lose your resources, right, because like something is idle basically half of the time. And TensorFlow datasets also allowing you to prefetch things, right, and after you run it like in parallel, so you basically make it like twice faster at least. The same goes like for running things like in parallel, so you can preprocess things like even faster. Additionally, if you're gonna go for more specialized hardware as tensor processing units, right, you also cannot really work with I don't know, some like more simplistic like in-memory NumPy arrays, right, and you actually need to in order to scale with bigger data sets, you actually need to use like TensorFlow dataset API. So it's actually worth investing because you're going to see like benefit on all iterations that you're having there. And in general, all of this like dataset API is getting like more richer and more nicer. So for instance, like Keras also added preprocessing APIs that allow you to do some tokenization for text or some other stuff for images. So it might be also worth looking into that. Okay, so now a couple of simple examples just to get you back to machine learning track, right? So imagine we have this like two sequences, right? And basically every couple is like more input and output, right? And you need to, like find some algorithm to do that, right? So if you were looking enough at those numbers, you can imagine this is actually Celsius to Fahrenheit conversion, right? And how you can do that as a developer, you can build a function, right? A formula, because we're all domain experts like in temperature. But in reality, if you want to go like machine learning approach, it's kind of like another way around, right? You have some inputs, you have some outputs, and you have some network to actually learn it, right? If you're going to look at it like more in Keras world, right, it's basically as simple as saying like, hey, I have like a sequential container. Sequential in this case means like output of one layer getting as an input to the next layer, right? And after you would like to have like one new unit in this layer, because the problem is like very simple, right? But gonna look at it like internally, right? You have some inputs, say multiplied by those weights. That is thing like Marc also explained to you. It has some biases, and after it gets like output, right? So like if you just like see it like as a layer, it's basically the same situation, right? You have input in Celsius, right? It's multiplies with your weights, right? And after it's adding like some biases. So it's like very well fitting to our problem. But again, it's just like examples that I brought in here. What you need to do afterwards is just like compile a model saying like, hey, how the model would know how wrong the model is, right? In this case, we're using like mean squared error, meaning like that we're taking square difference between what model predicted, right, and what do we see like as a target, and we're taking like a mean like against this like patch, right? And we have optimizers that's actually doing solving this optimizational problem for us, right? If you look at more on bigger scope, right, all of this problem is essentially about us having like network, right? And here you can see like from blue ones, it's more like input, closer to the input, right? And green ones is more like output, right? We're getting whatever task we have at the hand, right? And after we're trying to compute like, hey, how wrong the network is, right? And in the beginning, when we start with more or less like random values, random initializations, you can be like really super wrong, right? And after we're trying to propagate this error back, right, and fix it layer by layer, that's basically what backpropagation actually is about, right? Without going much in details, because Marc already did mention it, we have gradient descent that just like trying to imagine this is a function of of this like weights that we're having, right? And inputs, and after we trying just to find where is a minimum, right? Minimum in this case would mean where the loss is like the smallest, right? Where you're making the smallest amount of errors basically there. And if everything goes good and you don't have like any errors in this regard, you would see that your loss over time with number of epochs is going to get like smaller, meaning that your network is like learning something, and after getting like more and more correct answers for the questions that it's having. yeah, and after you can do some inference, you get some, like answers. And yeah, it works for this like super simplistic problems that I brought, but at the end of the day, it's not very different if you take, images basically, or like any other problems, right? Here we have pixels of this image, right? We're trying to normalize it to be like from 0 to 1, right? Because networks better working for, yeah, like those smaller numbers, basically. You have some weights, right? That network gonna learn, right? And it's like yielding some results, basically, right? After softmax, right? And the idea of that basically is that we essentially trying to find a good combination of weights, right? Just like W's, right? That would allow us, in most of the cases, say like where cat is cat or the digit is digit and stuff like that. In order to have it on more like a Keras side, it's also like pretty similar to what we have seen before. Again, we're saying like, hey, we have this like sequential container, meaning that outputs of one layer is getting as input to another one. We have one layer that is like flattening that, meaning that it's getting dimensionality 28 by 28 by 1, because we have grayscale cats. And after it has like hidden layers, 128, and we have like output layers that has like 10 of them, right? And yeah, it doesn't look like very super fancy, sophisticated, but even this one is like able to get some learning, right? And again, as we learned before, right, we need to again compile this model and say like, hey, how do we define what is like this functions that we're going to compute, yeah, how wrong we are. In this case, we take like a space categorical cross entropy, and we also say like what optimizer might be helpful. Yeah, and after it all works good, right, we're going to see again like losses going like down, what you see like on those graphs, and accuracy going higher. How to see those numbers? There's like a tensor board that also you can run with, in Colab itself, right? So, and the big benefit of tensor boards that you can see like in real time how numbers are changing, right? Because like if your epoch takes like some time, and after you need to run like for 10 epochs, in old ways you need to run for like a long time, and after you can only see results, and with tensor board you can see it like in real time, so you can see if it's actually learning. Okay, so but can we do it better, right? Because I mean, writing some networks of like some unknown architectures is like pretty hard, right? And turns out we can, right? We can stay again on shoulders of giants, right? And where is it coming from? So for quite some time we had this research competition called like ImageNet challenge, right? And the idea was that we have like huge amount of images, right, and more than 1,000 classes, right? And after different research institutions were kind of competing to say like who can build the best like network or whatever like algorithms that can classify those classes basically with the smallest amount of errors, right? And it's kind of cool, right? I mean, some researchers doing some competitions, but how can it be helpful for us, right? It turns out it could be, right? Because if you can look around, especially for vision problems, right, you can see that all of our objects kind of like are following the same nature of this planet Earth, right? Because we have, I don't know, gravity, we have some physical laws, right? And they're like pretty similar, right? So in order to us to learn classify cars and learn classify cats, right, we actually have like very similar vocabulary to talk about that, right? And if you would have like a network been trained for like lots of more than 1,000 classes, right? Turns out if you would look at different features, what they activate for of different layers, right, you would also see like different patterns, right? So in this regard, something closer to the left, right, is basically more closer to the entrance layers, and they would pick up things as colors and different simple contours and other things, right? So they will be activated if, let's say, there is a blue, right, or there is a effect like this. And if you're going to go more to the right side, you would see that those feature descriptors or feature extractors, essentially, they're going to get a bit more advanced, right? How might it be helpful? And it might be helpful in the following way, right? Turns out if you have, such pre-trained network, right, it allows us to define a problem, not in terms of like learning those feature descriptors, right, but just reusing them, right? Because we can imagine that on Earth, in, like normal things like for people, they look kind of alike. And after our network, especially if you just like transfer this part, can be like, this, for instance, node activated for lines. This is like for ovals, this is for triangles. And after the next layer, getting those simple constructs, right, and getting something more complex. So you can say, hey, is it like a fur? Is there like two eyes? Is there something else? And after you defining a dog, right, would be like way easier, because you don't need to train those like early layers, right? You can just say like, hey, what are the weights of this like having eyes? Or, I mean, this is like very simplistic example, but you just basically need to train more or less like last layers basically. So it's like way easier for you. Yeah, that also means that the amount of data that you need for that is like way smaller. So you don't need to have like 60,000 images to train like a simple like a dog classifier or whatever problem you have. You can do it with a couple of hundreds essentially. Yeah, and it's good, but you still need to have like find some models, like, and you'd be like, hey, where do I do that? And it's like really complicated on what data set it was trained. That's why TensorFlow some years ago released on TensorFlow Hub, right? That allowing you essentially to look at those different pre-trained networks and reuse it like somewhere else. So for instance, you can have some image feature extractors, right? Or something like for text as BERT, or even like object detection. And after you can kickstart your project like way faster without actually needing like a big data set and like starting from there. Here I have example of me actually, there was like a feature on the Twitter, and I built like a small like a car prediction. So you can build like a tiny, is there like a available parking lot for you, right? And it's like really straightforward, right? Because it took me maybe like 2 hours or something to get it running, and not even data, because like cars were already like a part of the model that I was using. So it can be like way simpler. So how can you do that? So you have seen already those like sequential Keras models, right? And unfortunately, something to keep in mind, right, that all of those networks, right, they're usually trained with some, having in mind different dimensionality of images. So in this case, we have like 224 by 224. And if your preprocessed like data is smaller or bigger, what you can do, but again, it's like not for production examples, you can put like a Keras lambda layer, right, that would resize your images to the size that you would like to have, right? And after, again, you have like resizing here, you do this like Keras layer that does like some feature extraction, depending like which one you would like to have. And after you're saying like, hey, I'll have only 5 types of the sneakers. So this is basically, like activation softmax and dense layer for that. And that's it, right? In one screen, you can build like your sneakers prediction pretty quickly, pretty fast. If you want to have something more advanced, you can also go like extra mile and say like, hey, the layers that were pre-trained, right? Maybe I wanna, like unfreeze them, right? Because in the initial case, you basically have the setup where you just like take them all as they are, right? And you're only training like your like last couple ones. But usually it's a good practice to start it with like one learning rate. And once you're getting like into some, convergence point, you actually start to unfreeze a bit of layers with a smaller learning rate, right? So you maybe like learn some high-level features that are specific for your own data set, right? Why do you need to do it later? Because if you do it like in the very beginning, right, you might essentially override those feature descriptors that were learned like on hundreds of thousands of images, right? So you need to be like really careful, like what do you do there? If you're coming again and you wanna be like even, hey, I wanna make it even simpler, TensorFlow also released like what's called Model Maker, right? That I think originally targeted more for mobile developers. And if you can see my impers like on the screen, it's allowing you to get like the main parts of like a pipeline in relatively like simple fashion. So you can say like, hey, I wanna my images like living in the folders, right? And I'm gonna use like image data loader, right? And there is task for classifier. So you can essentially create super simple like image classifier with like one line. Obviously, it doesn't work really like for all cases. It's just like to get your hands dirty. And here we also like reusing like a hub Keras layer. So it's very similar to what you did before, but you need to like write even less lines. And more in general, all of this is basically going in the same direction, that something that like look like very sophisticated is like, hey, you can ask something in text, right? You can ask a question in text about image content, right? And it used to be like really complicated problem, but now you can say like, hey, I would like to extract feature from images, right? I can do some sentence encoding, right? And after you just like training majority, basically like last parts of that, right? So you can reuse some blocks and get results like way faster with like less resources invested in that. Yeah, and in general, as I mentioned, TensorFlow as ecosystem, right, allowing you to on one hand like train those things, right, with Hub and Keras as API to run execution like in different like hardware acceleration, but after it allows you to save those things. So you can run it in different environments, right? So here's just a couple of examples for TensorFlow Lite to run it on mobile, or TensorFlow JS to run it like in browser, or even like on hardware. So at one of examples that I brought to you already, like about those healthy food, I actually deployed it to like a small hardware, so you can potentially hang it like in front of your dining table, and after it will like every time detect like if you have like healthy food or not healthy. So it's pretty cool. Plus there's like other tools like as ML Kit, as a part also of Google, that allow you to deploy those models like very easily, right? So you can only trigger it like where user has like Wi-Fi, right? And again, you don't need to focus on software engineering and how to build a system. You can just reuse some blocks from Google that will do like automatically for you. If you want to run it like more on the server side, you can use like a TensorFlow serving, right? It's also allowing you to get some REST API for your models and some predictions. And for TensorFlow JS, as I guess like Marc also mentioned, there is also converter tools that allowing you to export your Python pre-trained model into like JavaScript compatible model essentially. If you use it like in production, there's like TensorFlow Extended that allowing you to focus like on every step, right? To do like some data validation, to do, I don't know, like model evaluation like afterwards, and it's like pretty helpful. Plus you can also validate what is the distribution of this data. So you don't really have like unfair models because you don't really have just like enough data for those segments. Yeah, and now a couple of like last examples just to wrap it up. If it still looks complicated, right? There is a project from Google called Teachable Machines, right? So it's allowing you just like in browser collect like a small data set, right? Train the network, right? And after export it, like I said, like a simple model. So if this one looks like too complicated for you, just go ahead and look at this one, and you will build something definitely like in matter of like 1 hour, like it's collecting data and everything else. So it's pretty cool. And they have also example of those like candy starter. So maybe something that you want to play with current time as well. A couple of small examples that they build in a matter of like hackathon. So basically 24 hours or something. One is basically based on general adversarial network again, like GANs. So I had some setups that can basically convert a model like a picture into contours, right? And after network would be able with picture to picture, pix to pix, basically able to, based on the contours, generate some images, right? So what you can do like as extra mile is what I have seen on one hand. You see like this original image, right? And after I'm changing it to have it a star, right? And after this star would actually be generated on real image, or I added like a heel, and after this heel also going to generate like an image. So what you can do from there, given that you now know the notion of feature extractors, right? You can try to extract the feature from those images, right? And you have like big e-commerce platform, for instance, and you will find something that might look something alike in that direction, right? So again, it's allowing you to prototype things like pretty quickly. Or another example that I was believing that, if people posting something on Instagram, right, they might be interested in this like lifestyle type. So I trained like a small like classifier that would, given the images that you have, like recommend you some brands, right? So when I went kayaking, I had this image, and this is like suggesting that maybe I should take a look at Patagonia. So that might be helpful, right? Or here's another example for Gucci. That also has Patagonia on the 3rd place. It's pretty interesting. So if you're interested, as was already introduced, I also organized machine learning meetup in Munich. And since nowadays we do quite a bunch of events like online, and we're gonna have like next one about computer vision on Raspberry Pi. So if you want to get a bit more your hands dirty with like how to do this hardware, you're more than welcome. Just like to wrap it up, is it like that simple and you can build something just in a couple of hours? Yes, you can for first 60%, maybe 70%, but every next percentage point is getting like harder, right? That's why we have people who like officially called like machine learning engineers, right? And they actually spend quite a bit of time to optimize to the best performance, right? And there are like many really like technical things that are like complicated for like last mile delivery. So do appreciate these people, and if you really like this, can also get in that direction, because it's like really exciting to build something like that. And as already was mentioned by Larissa before, all of our machine learning, right, is based like on data, right? So we need to be like really careful what data we looking at, right, and what models we build upon, right? Because like if model has like some biases, right, guess what? Like your model can be reproducing the same biases. But what makes me like more optimistic, right, is data is kind of more standardized, right? So if you're finding those issues and we're improving our data over time, we're going to get like better and better. So this is like way more gradual approach, right, to ensure that like in 50 years, right, we're definitely going to be in a better place than we are right now. So that's why I'm like really hopeful that we're going to end up like in a good place. Yes, with that, I'm done with my part. Here you can see my Twitter account. So in case it was too fast, and it was pretty fast, feel free to approach me, right? And I'm more than happy answer your questions like on any part of this presentation, because generally speaking, you know, like when I do like a workshop about that, it also takes like quite some hours to actually go like in details about every part. So if you have some conversation about like any particular slide or questions that you have like on your mind, feel free to approach even or now or later, basically. So it's like all open, and especially those days when we all like in quarantine, I guess it's like, yeah, it's easier to answer those questions because we don't need to run away from one place to another. With that, I'm open for questions.
Great, thank you, Sergii. So yeah, we have run over a bit, so I'm not so sure how much time we'll have for questions. But as you say, we've linked your Twitter there in the description. So if you do find any questions in the next couple of hours, then please do ask Sergii. And yeah, so we should now talk about the party, which will be happening in about 5 minutes. I'll just put the link on the screen now. So there's the link. But yeah, in the meantime, thank you so much, Sergii. We hope you have a great evening. And yeah, again, please ask Sergii your questions.
Thanks for having me. It was amazing.
Thank you. So with that, we conclude the talk for the ML track. We'd like to thank all the speakers, Marc, Larissa, and Sergii, for joining us tonight and giving very informative and interesting talks. And thank you as well, our audience, for joining this dev party and interacting through the chat and giving your questions. It's been really great to interact with you.
Definitely, but the dev party is not over yet. The discussions are still going on Slack and Twitter, but please also join us at the after party. You can find the link in the description box of this video. At the party, we will announce the winners of our social media competition. So make sure you tweet any last tweets you have using hashtag GDG DevParty for the chance of winning one of 3 prizes. Please also keep the discussion going and the questions coming on Slack. And thank you all again, and see you at the after party.
Thank you, everyone. We'll see you there.
Bye.